Okay, good afternoon. So, before I start, there's some more material which is I have uploaded because under the interaction, two more lectures. These we'll do in next class 3 and 4 next week. Sorry, under offline. Sorry, under interaction. Anything else? Recording is there already. You can check on YouTube tutorial lab. This will be for Thursday, 4:30 to 6:30. I think the room number is probably not communicated to you, so I'll email you, right? Is it written on the timetable, the room number? Okay, it's not there, na? So I'll email you today a general welcome email and then I'll list all of this. Under the offline category, I've uploaded 4 more materials. This was for ANN Artificial Neural Network. I have uploaded a PDF on gradients and Hessian and Taylor series. This is typically we do in our optimization course. What is an positive definite matrix, characterization for that, what is a convex set, what is a convex function, and then what is a pseudo inverse of a matrix. So these 4 things the CS undergraduates already know because we have done it in optimization. You guys can go over it offline. We'll keep referring it in the class today itself when we go along. But next week, Wednesday, I'll take a lecture on optimization, first lecture for the non-CS undergraduates. Hai na? There I'll cover some part of it and basic of, but you can still go through it. It's straightforward, it's written well so that you don't get lost in the class. I've also uploaded this practice set on neural network and regression, which you can try it on your own. And then under the homeworks, 2 homeworks are there which we'll refer today in the class. All the material has been uploaded. So with the start the first topic. So like, have you opened the tab, writing tab? Okay, thank you. How to put the 2 of them parallelly? The PDF and that, to drag it in. Okay, yeah. All right. So we are starting linear regression and correlation. So like we said, this is part of the geometric model. Okay. So please don't talk when I'm talking, hai na? Finish your talking before I come or I give you time to work out, then talk, hai na? It distracts me. Another thing is for the attendance, we carry the attendance for 2 reasons. You must be wondering why are we carrying. I know that you guys do proxy attendance for each other. It doesn't get you any marks, by the way. One thing is it is needed by the academic office to maintain an attendance log of who's coming, who's not. Another reason when I look at the attendance is when I have to decide between the AA and the AB category. So if you know, like I said, 15% are only allowed in the AA category. So if there'll be a tie or something, so then I'll look who has been attending and who has been absconding. So then in that case, the person who has been attending will be pushed to AA. So at that stage, I look at the attendance. So in case, otherwise, I don't give marks for attendance, but academic office does want us to keep a log of attendance. So that's why we collect. Okay. So we are starting the first, like we said, geometric model. This is too thick. How to make it thinner? It ran away also. What did I do? Is this one? It'll turn out to be red probably. So that's the color. Acha, thickness, okay. Thank you. So we're starting with the, make it a little more thicker. Okay, this is better. So we're starting with geometric models, and like we said, so this is what I mean by scribbling. Although the slides have everything, but I'm going to write on the side of it so that I go slightly slower. So the very first topic that we are going to look at is regression. So in regression, there are multiple parts. The very first part, so this is the first thing which we are doing, and my focus is only on geometric models. So regression, SVM and distance model. So first we'll look at correlation. Then what we are going to look at is one-dimensional regression. Then what we are going to look at is multiple dimension regression. And then what we're going to do is to solve these multiple regression dimension. All that is in the slides. We have to do it numerically, and then which is by the gradient descent method, and then we'll have a closed form solution. And then what we'll have, so these are the two solutions of a regression problem. And then there is something which is very important, is regularization. So hopefully we are going to do, we'll see how far we go today. But this is what the plan for the lecture is today. Huh? Okay, so let's go here. Before I start on correlation, and what does the name correlation mean to you? You have to speak. Yeah, some sort of a relationship between two sets of variables, correlation, because you're relating two different set of variables. So to be able to understand that, you need to understand what is covariance. In case you have seen covariance before, that's okay. But if you have not seen it, then we'll go back to something called standard deviation, which maybe you've seen it in your school days even. So what is a standard deviation? So this is from Wikipedia I'm showing. Standard deviation is a measure of the variation or dispersion in the set of values. When you say how much, so this is for one variable when you're looking at standard deviation, how much it is dispersed or away from the mean. That's what it says. A low standard deviation indicates the value tend to be close to the mean, while the high standard indicates the values are spread out over a range. Everybody remembers this from 9, 10th, 11th, 12th, whenever you study statistics. An example of this, if you're given these set of data points, 2 to 9, what is written here, you first find the mean of that. There are 8 data points, you add them up, divide by the number. Then you find how much each point is away from the mean, and squared it, add it, and normalize it, and then you get your something called as a variance. The square root of the variance is called the standard deviation. So this is something we do it for one variable. If you've got two separate sets of variable, then what's the equivalent of a standard deviation is covariance. That is what I was talking about in the slides. We go back a coming back to the slides. So what is a covariance? So you can look at it. The covariance is you're taking the first variable, each component of it, subtracting it from its mean, taking the second variable component, subtracting it from the mean, adding them up, and normalizing it. Now this normalization, which is done in the denominator, that varies from books to books. You can do it by n, you can do it by n minus 1. The one which I am following is n minus 1, so I'm sticking to this. You can also do it with n, doesn't matter. Hai? So this is what is something called as a covariance. Now what does the covariance mean? Covariance means that if the value turns out to be positive, the two sets of variables which have different values are positively. If it's negative, they are inversely correlated. And if it turns out to be 0, there is no relation between them. What are we trying to do? We're trying to make sense of the data which is coming in different dimensions to us, right? It's coming in X and Y directions. So to make this thing unitless, because this will have a unit of X and Y, because remember you're doing X into Y here, the two variables, you do something called as a Pearson's correlation coefficient, which is written on here, which means that you take the covariance of X and Y and divide by the two standard deviations or the square root of the variances, which will make your R to be unitless, which is just for the sake of convenience that you can work with it. Okay, so what do we know further about it? I'm going a little fast on this because this is pretty straightforward. When we come to regression and start deriving things, I'll start writing on the right side of the board. So if you read what's written here, it says that the Pearson coefficient varies from -1 to 1. And if it's towards +1, then it's saying that it's positively correlated strongly. If towards -1, it's negatively correlated. Some examples. So now look at the figure. Yeah. So if you look at X and Y, so here you can see the slope is negative. So which means that they are inversely correlated on the first figure, on the first row. If you look at the second figure, again, it's negatively correlated, but the points are more spread apart from this line which we have drawn, right? Which means that they are weakly correlated. And if it's a straight line, there's absolutely no correlation. If you look at the bottom row, this guy is positively correlated, strongly, weakly correlated, no correlation. The R values are written here at the bottom, right? So this is just to give you an idea. You don't need to always have linear relation. You can have curvy linear relationship, which is written in the next figure. The left column is all linear, weakly positive, weakly negative. This is curvy linear. Both, it has components of both positive and negative correlations as it's going along. Strong and weak, although I already told you, this is evident that when the points are closer to this line, which you have drawn for R, then they are strong. If they are spread apart, then it's weak. And again, if it's a straight line, whether it's weak or strong, it's no correlation. Calculating by hand, very basic even. I think you will learn this in the 6th, 7th, 8th grade. So R is covariance divided by the two standard deviations. You substitute those values. You can see that the n-1 cancels out. You can see here, again, there's an n-1. So if you were using n here, you would use n for both the variances and it will not matter. It will eventually go away. So your formulation would be that the Pearson coefficient takes the numerator of the covariance divided by the numerators of the variances and the square root of that. Everybody okay? Okay. Now, this was something which rarely we run into real life because often the two sets of variables which we know, the two data points, or which will now further go is multi-dimensional. You'll have x, y, z, theta, and so on, or theta 1, theta 2, all the way till theta n. They are often related to each other in real life rather than being completely not related. So in that context comes the idea of regression. So what is regression? So it's written here. Is it readable at the back, the slides? You have to tell me then. No, I have to zoom in. How to scroll? Maybe make this guy smaller slightly. Okay, it's better now. So what does it say? In correlation, the two variables are treated as equals. In regression, one variable is considered independent, the other is dependent. So what I did was I also have the dictionary.com definition of regression for you. So let's just read it. What does it say? So in statistics, a procedure of determining relationship between a dependent variable. For example, your success in college, this is of course in the US context they are writing. So the success in college is dependent on how much you have got in your SAT scores, which is the entrance exam for undergraduates there. or you can think of how much marks you've got, IIT, JEE or your GATE exams. So depending on your marks, that will probably determine how good you succeed in college. So this is the independent variable, this is the dependent variable. The success in college is dependent, the marks which you got in your entrance exam is the independent variable. The relationship is expressed as an equation in terms of a line or a curve, and so on and so forth, right? So this is the definition of regression. Let's go back. Okay, so this was the definition of regression. Now what do we do in regression? Classification is another type of problem which we solve, which we'll see later. Yesterday, those who were there, I talked about classifying images into breast cancer images, benign or malignant. Regression is it's a complementary problem to classification. That in classification, you usually have discrete value deciding into classes, whether 2 classes or 3 classes, and so on and so forth. Regression problem gives you continuous scale that you can always find value, which will be clear in the next few slides, whether you're doing interpolation or you're doing extrapolation of data. So this is what it's saying in regression. The output is, in classification, the output is nominal or discrete. In regression, the output is continuous. You use function approximation. And the simplest way is to do linear regression. Linear regression is that you have got, so this is your X is your independent variable, Y is your dependent variable, and these are the set of data points for X and Y. They're coming in pairs. We are working in 2 dimensions at the moment. Huh? So what we have to do, we have to find a line which defines this relationship, right? So what do we do? So we draw a line, so it says you can fit many model, which goes through the points. So you draw a line. In 2 dimension, it's a line. In n dimension, it will be called an hyperplane, right? So that is what's written, goes a hyperplane here. All right, so now what do? You take each of the points and then project it on this line. Basically see how far your point is from the line. Add all those distances up. Sleepy? Okay. After lunch, sleepy, I know. I've made them ready with a joke, which will probably wake you up, but we'll do it after half of the class. So what do? We take each of the point, project it on the line, and there will be some residues which will be left. Which means that ideally all points should be on the line, but you are far away from the line. So we'll try to minimize the distances and find that line which minimizes all of the distances together, right? That is what we are trying to do. Why do we use regression? Regression is used that these are the data points which are given to you. I can't open writing in this, right? I'll have to download it and open, hai na? Okay, that's fine, let's leave it. So ideally, let's say these are the points which are given. Once I draw the line, I have not told you how to draw the line. The rest of the lecture till end of the class today is figuring out how to get this best line out in a 1-dimensional setting and in a multi-dimensional setting. I'm sorry if I'm looking less here because I'm tending to look this direction. So if you want, I'm not ignoring you, you can sit more this side. Huh? Okay, so what do? You draw a line and then you want to say for a particular X, what's the value of Y? Then you will find a point here. This is called interpolation. That within a range of the data points, for the unknown data point, you're trying to find the Y value for a given X, is called interpolation. You can also extrapolate. Extrapolate by the meaning says going out of the domain, which means that if I have an X range from 0 to 100, and I know that Y values are varying from 1 to 1000 for this. Now when X becomes 200, what's the Y value? That will be extrapolation, assuming that your regression curve, or in this case the regression line, stays the same for outside the domain also. So that is what is drawn on the next slide. You can see this is a curve which we have drawn. If A and B were the measure point, in between you're finding, it's called interpolation. If you are going outside, for example, you have data from 12 to 14 and you're going outside the 14 to 15, then you're doing an extrapolation. So there's an example for this. This is an example where it's saying you're giving medication to a person and doses in mgs or whatever you're giving, typically milligrams. and the number of patients cured. First two columns are important. Total patients is also given to you, and then you're finding the probability of patient cured. So this is 1/5, 2/6, 4/6, and 6/7. So this is what it's computed. You plotted this in a figure. This figure is slightly adjusted to the right. Basically, for 20 milligram, 1 is cured, 4 are not cured. For 30 milligrams, 2 are cured, 4 are not cured, 40, and so on and so forth. So this is how this is built. And then based on that, you build the probability which you have computed in this table. You draw a probability graph as well. So this is 0.2, 0.33, 0.67, 0.86 for 20, 30, 40, 50, 60, and so on and so forth. So again, this you put the data points so that now you can build a regression line. Once you have built the regression, right, so then you can tell whether you're giving 25 mg of dose, then what will be, how many patients will be cured. Or if you give 75 mg of dose, how many patients will be cured. It's very straightforward, nothing too deep. Another example to highlight dependency and independence is this one, that if the relation between the rainfall and the umbrellas sold. So it's saying if, you know, for example, if it's too much rainfall, then there are more umbrellas sold. So again, you can take this, put that into a regression equation, build a regression line or a regression curve, do the interpolation or extrapolation. Okay. So now coming to more mathematical thing, we start with the first thing. So this, what we have seen is correlation, and now we are going to do simple one-dimensional linear regression. So now assume that there is one input variable x and one output. If there are multiple dimensions of input x, then we call it as a multiple linear regression. When there is a multiple output variable out, then we call it as a multivariate linear regression. So basically there could be number of dimensions of both the independent and the dependent variables can be large. When the independent variable is large, the terminology or the nomenclature is called as a multiple linear regression, and when it is done for the y, the dependent variable, then it's called as a multivariate. It's just that. So we're going to see the first case here today, the multiple linear. Okay, now before I tell about this sum of squared, I'll use this guy, make it slightly bigger so that you can see. Okay, so let's say these were my points, and this is the line or the regression line which I'm trying to identify. I have not figured it out yet. Huh? I'm showing it you in 2 dimensions. So what you'll do, you'll project these here on this. So there'll be a residue here, a residue here, residue here, and a residue here. So let's say these points are 1, 2, 3, 4. This is the x direction, this is the y direction. The computer science people who have taken undergraduate, have taken optimization, could recall the Gauss-Newton method. We used this there, the least square problem, but nevertheless I'm going to repeat it. So you've got the data points as x1, y1, x2, y2, x3, y3, and x4, y4. These are given to you in pairs. And for each of these are the projections on which these points are following. So you've got the corresponding y1 hat, y2 hat, y3 hat, and y4 hat. Which is y1 hat is this, y2 hat is this, y3 hat is this, and y4 hat is this. This is the predicted value because you are predicting it based on the, so if this is x1, this is y1, this is y1 hat, so and so forth. You can figure this out, right? Rest of the, on the figure. So now the question is, you have to find a line which minimizes this for all of them. Everybody agrees? So what do you have to do? You have, is this readable at the back? At any point it gets unreadable, then please stop me. Hai? I may forget in the flow. So you want to minimize y1 minus y1 hat. Correct? You would also want to minimize y2 minus y2 hat minimize y3 minus y4 and y3 minus y3 hat and y4 minus y4 hat. You want to minimize all of them, correct? And which one is larger? I don't know. In the figure, this figure, it is evident that y1 is bigger than y1 hat, but ideally you would not know. So what you could actually do is put an absolute sign on all of them. So this kind of a problem is difficult to solve because you've got multiple objective functions to minimize. Does everybody agrees? Since I've got 4 points, I'm getting 4 objective functions to minimize. Can I make a simpler optimization problem? So the answer is yes. What if I squared them and add them? So if I do minimize y1 minus y1 hat square plus y2 minus y2 hat square till y4 minus y4 hat square. What will be the minimum of this objective function? How much minimum it can get? 0, right? It's the sum of square of variables, so it can't get less than 0. So the minimum value it can get is 0, and in that case what will happen? All of them have to be 0. The individual values have to be 0. Everybody agrees? Otherwise you can't. If one value becomes negative or positive, it cannot reach 0. So which is all y1 minus y1 hat, y2 minus y2 hat and so forth, all will tend to 0. Only then it is possible. So hence, instead of working with multiple objective problems, we make a simple objective function, one objective function, independent of the number of points you are taking, and we do it by taking the difference of the predicted value and the original value, subtracting, squaring and summing all of them and minimizing the whole thing together. Everybody with me? Yes or no? So this is what is written in the slide which I just showed. I think we can make it bigger. Probably I don't need them parallelly for now. So this is what is written here for a simple linear regression. So there are many ways of doing this. This is one of the ways. This is what we did in the Gauss-Newton method in the optimization course, those who were there. So sum of squared error, which is predicted minus actual or original square, which is called as the residue square. Okay, so this is how we define it. Now, to be able to do that, okay, let's go back. So this is, I'm motivated doing the least, so this is called as the least squares problem. Why? Because you're squaring and you're minimizing that, summing it. So you're calling it as a least square problem. So now to be able to get these y hats, you need to assume the equation of the line, correct? So the equation of the line, what do you know from your basic is y is equal to mx plus c, correct? From your coordinate geometry from your school time. So this is what is written here. This is written alpha plus beta, but this is basically y is equal to mx plus c. So this is your y and this is your error and this is your predicted value, this is your actual value. The y, don't confuse with the hat, you're referring to that. So you remember y is equal to mx plus c, or it's written mx plus b. What is m? M is the slope of the line and b or the c is the intercept where it's intersecting the y-axis. So it's written this is b, m is the tan of theta or this about this. I don't know why all this is there, it's too simple to tell. A slope of 2 means that every 1 unit change in x is also 2 unit in y. All this you know, right? So basically 1 unit change in this leads to 2 unit change here, which means that the slope is 2 or m is 2. Okay. Now how do we learn the parameters? Now what are parameters here? So this will start coming often in machine learning. Parameters are something which is unknown to you from your model. We call them as parameters. What is your model here? Y is equal to mx plus c. So what are your parameters? M and c is the parameter, and in this case m and b is the parameter, or alpha and beta are the parameters. Initially we wrote it as alpha plus beta. Right? So we're going to now learn them. When we say learn them, which means that given a set of points, we are going to figure out what the value of these is, which means you're learning it or you're training your model. This is the terminology which we are going to use. Okay. All right. So how do we learn the parameters? So we are going to take the difference between the actual and the predicted, which we wrote on this. Right? The difference between this, and we are going to find the minimum of that, right? So we go back to the slide. So you're saying you're taking the difference, yi minus beta xi plus alpha, you're doing the difference square, and now you're actually summing it also. This is not working, I'll download next time and then write. So you're summing this and then you're trying to minimize this. So what we are going to do is we're going to individually, how do you find a minimum of an objective function? Or how do you find a minimum of a function going from one dimension to one dimension? So let's say you've got f going from one dimension to one dimension. So in the optimization, we'll make this n and we'll see more as we go along. So what do? To find the minimum value of this, we say f prime is equal to 0 or df, if f is a function of x, df over dx is equal to 0. What will this give you? It will give you the candidates for minimizer, and then you find f double prime. You find that if f double prime at that particular point which you have found is greater than 0, then you say yes, it has found a minima. This is coming from your basic calculus. So now what do? We take these differences squares. So in our case, it is not a function going from one dimensional to one dimensional. It is going from how many dimensions? 2 dimensions to 1 dimension, because there is alpha and beta here. There are 2 variables which you are trying to find, remember? So if you recall, your function is f is equal to minimize of yi minus alpha plus beta xi square summation I going from 1 to n. Correct? Yes? Okay. So again, we were still in, your x was one dimensional and your y was one dimensional. Remember that, right? We have not changed the dimension of x or y. We are still in a one dimensional regression which we are trying to do. So what we'll do is, we'll take individually each of these and try to make it equal to 0 and try to find the values, right? So that is what is done on the slide. Okay. So to find the minimum of the sum of the squared differences, so what do? We take with respect to beta now, generalize this to the n dimensions. When you're trying to do it for one dimension, you're taking the full derivative with respect to x. Here x was the variable, right? But now, sorry me. Kuldeep, what did I click wrong? Looking at the pen. Okay, pen, it's true. Okay, so let's not call this f, because you will get confused with the f there. Let's call this some other variable g. G is a function of alpha and beta. Everybody agrees? It's a function of alpha and beta, because x and y are the known values. Those are the data points which are given to you. For x1, what's y1? For x2, what's y2? For x4, what's y4? So the unknown is the line, the parameters which you're trying to learn. So to do that, what we'll have to do, can we write dg over d alpha? Again, I'm going too basic, but can I write this? No, I can't. Because you have to find now partial derivatives, right? Because it's a function of 2 variables. So what do? Am I going too fast? Everybody's okay? So what I'll have to do, I'll have to do dg over d beta, and I also have to do dg over d alpha. Correct? And once I put them in a vector format, whether you do it with respect to alpha first or beta first doesn't matter. Let's say I'm doing with respect to alpha, so I'll say dg over d alpha, dg over d beta. This will, I'll call it as my gradient of g. This is the generalization of the derivative for a function of many variables. So this f prime, because it's a function of one variable, is the derivative. When you have a function of multiple variable, it becomes the gradient. So now what do you have to do? You have to make the gradient equal to 0. Everybody agrees? Yes or no? So we'll go back to the slide and do the same thing which it's doing here. So I'll go back to the slide. So what do you say? Find beta. So here it's doing with respect to beta first. You can do it with anyone. You do partials with respect to beta of yi minus beta xi alpha I. The 2 will come in front. You'll differentiate with respect to beta. So the minus xi will come and you'll get this is equal to 0. Similarly, you will do it for alpha is equal to 0. And then once you do that, you will get that beta hat or the ideal beta is this. And alpha hat, the ideal alpha is this. So I've worked this out in the homework. You go ahead and check. Right? So I'll show you how to work this out in the homework. So this is where it's worked out. The same thing which I said, y is this, you minimize this. Here I've done it with respect to alpha first. I'm calling this as alpha hat and beta hat because these are the parameter value which minimizes the function. So to make it a specific value, I'm putting hats on it. So don't get confused. So you get alpha hat as this and then you put it and substitute a lot of substitution and then you'll get beta as this. So go home and work this out. Basic algebra, nothing new. Everybody with me? Okay. So we'll go back to our slide. Okay, so make it bigger and go to that particular slide. So we got these values. What have I missed here? Before I move on to the multi-dimensional regression case, this was one-dimensional regression. Why? Because x and y both were one-dimensional, remember? Now we'll go to the case where x becomes multiple dimensional, the multiple simple regression or multiple linear regression. If we make y also multiple dimensional, it will be multivariate. But my question is this the minimizer or is it a candidate for minimizer? Okay, the CS undergraduates I could hear, these are candidate. Others, is it a minimizer or a candidate for minimizer? How do you figure out whether it's a candidate for minimizer or a minimizer? How do you figure that out? Not the CS undergraduates, others. How do you figure out whether it's a minimizer or it is a minimizer or it is a candidate for minimizer? What's the difference first of all? What's the difference between the two? यहाँ क्या हो रहा है? When you take, this is basic calculus from your first, everybody has done first year calculus, everybody, even the sciences people have done, yes or no? They tell that if there's a function of one dimension, when you find the derivative of that, make it equal to 0, the value of x which you will get here will be the, let's say x is equal to x naught. This would be the candidate for minimizer. To actually tell whether it is the stationary point. It can be a minimizer, it could be a maximizer, or it could be the point where the inflection happen. You know, it could give you something like this. I mean, at this point also the derivative is 0. When it's going down, the derivative is 0. When it's going up, the derivative is 0. So the derivative is 0 at many places. Doesn't mean that it is a minimizer. Yes or no? What do we do to tell that it is a minimizer? We find the double derivative. That's what I was asking you. These guys understood because they've just taken the optimization. So you take the double derivative. The double derivative is greater than 0. Then we say at x0, let's say at this point, then we say x0 is a minimizer. Until we don't go to the second derivative, it remains a candidate for minimizer. Everybody agrees? So now coming back to our problem. To this problem, I made gradient of this individually, made it equal to 0, and I was able to tell you that this beta hat, ideal beta hat, is covariance divided by variance. What's the value? Xy, and alpha is y minus beta x. Covariance of x and y divided by variance of x. And then we say this is something which you would derive at, go through do it yourself, then look at the algebra worked out in the homework, and then you should be able to get it. This is x is y minus beta hat x hat. These are bars. Bars are the mean value. That is what we are referring, which you would derive and understand. So I asked that are these candidates for minimizer or are these minimizers? Now you can tell. These are candidates because I just made the first derivative, in this case the gradient, equal to 0. To be able to tell this is a minimizer, what do I need to do? Find the double derivative. What will be the double derivative in this case? It will be the Hessian, right? So now these guys know, you guys don't know. So I'll again go back to the material which I just uploaded. Go home and read it. So let's go back to the material uploaded. Offline supporting material, gradient and Hessian. So gradient I just told you, which is there. What is Hessian? Hessian is the characterization of the double derivative for a function of many variable with multiple y values, right? So if f, so you can see it, you can work this out. So I'm not going to go over this today. I'll go over this in the next class, which will happen the following Monday, because this chain of thought will continue for 2 more lectures. So before I go further, go ahead and understand Hessian. Please read it and do some problems also which are there about Hessian. Okay, so let's go back. Coming back to, I think I should download all of these and not switch between. So what we did was, we found the candidates for minimizer for a one-dimensional regression problem, which is this. So what I just said is, in this case, you will compute the second derivative equivalent of f double prime, second derivative equivalent of g, which we'll call it as the Hessian of g. The Hessian of g, which those who will go in, is called the Jacobian of the gradient of g. What it says is that you go and take each of the elements and differentiate with respect to all the elements. So if I have got the first element of gradient of g as dg over d alpha, I'll differentiate with respect to alpha with respect to beta and put it in a matrix format. So this will be d2g over d alpha square, d2g over d beta d alpha. Correct? Then what I'll do, I'll take this second element, which is this guy, and differentiate with respect to alpha and beta again, because those are my variables. So this will be d2g over d alpha d beta, d2g over d beta square. Now I'll do this. So if this matrix turns out to be positive definite at this, which is the characterization of saying that a function of one variable is greater than equal to 0, then it is a minimizer. Does it make sense? Now what is positive definite? Again, have you taken linear algebra? Do you know positive definite? Yes or no? You have to be loud. Whether no should be louder. So again, going back to offline supporting material, the next thing is what is a positive definite matrix. So go ahead and read this. I assume itni math so you'll have to know, unfortunately, for the class. So you'll have to learn as you go along, those who are not coming from that background. So go home and read about it. Okay. So having said that, I'll go back to our interaction lectures again, intro. Okay, so in this case, what will happen? This Hessian will turn out to be positive definite. Now, if you have time, go ahead and check it, but we prove this in the multiple regression case. I don't prove it in this one-dimensional regression case where x and y are one-dimensional. The next thing which I do is do the multiple regression case, and there we actually show. Everybody convinced? So what did I do? I'll just summarize it. The next thing which I start is multiple linear regression, which will get a little more hairier. If you have not understood it, then this will be more difficult to understand. So I'll just summarize. What did we do in the one-dimensional regression? We took x and y to be one-dimensional. We had given set of points. Typically, the number of points which we assume are n. That's the variable which we use to define the number of points. To define the dimensions, we usually use d. So here d was 1 for both x and y. We had these points. We had to find the line which best fits these lines, which means that these points are projected on the line, and then you find those residues, you square them and add them because you wanted to create one objective function, and then to find the minima of that, you take the derivative of that, make it equal to 0. In here, alpha and beta were the learning parameters. It was two-dimensional problem, so I had to do dg over d alpha, d beta over dg over d beta equal to 0. I was able to find beta hat and alpha hat, which are the values which are candidates for minimizer. Beta hat turned out to be covariance of x and y divided by variance of x, and alpha hat by substitution is y bar minus beta hat times x hat. So that is what you found. But these were still candidates for minimizer. When you take that g, find its Hessian, which I had shown there, that will turn out to be positive definite at this beta hat and h hat, which is a characterization saying this beta hat and alpha hat are the minimizers. Everybody okay? Okay. Now what we do, we make the complexity slightly more harder. We increase the dimension of the x. So now you still have n points, x1 to xn and y1 to yn, but rather than putting them as subscripts, we are going to write them as superscripts. And the dimension is going to be written as the subscript, right? So this is what is written on this slide. Did you send any joke? Oh, it's already 24. Okay, no, there's no break here. I thought some of you were still sleeping. Hindi is okay. This is a question every time I get, then I have to translate it in English and it loses an impact. So the teacher, विदेश में 15 साल के बच्चे अपने पैरों पर खड़े हो जाते हैं. चिंटू मास्टर जी हमारे देश में तो 1 साल का बच्चा भागने लगता है. आज के टेस्ट में तुम्हारे कितने नंबर आए छोटू? मोटू से 20 नंबर कम पापा. अच्छा, मोटू के कितने नंबर आए? छोटू 20 नंबर. Well, the name Motu and Chotu in itself is humorous, like Santa and Banta. Okay, come back. We're not done yet. Do you have a lecture after this? Okay, at least let me reach to the objective function, then I'll stop. है ना? Just 3 more slides. We have got 6 more minutes. I think 5 more minutes. So let me just try to finish this. So let's focus. So we're talking about multiple linear regression, where we are saying you've got x1 to xn. The quickly you stop talking, the quickly I can finish. है ना? So the superscripts are the number of points, and then subscript we'll start adding for the dimension. So you can see this is 1 to n, and each xi is belonging to d dimension. Y's are also y1 to yn because they have to map, but they are one dimensional. Ignore the figure, it's just referring to a linear regression or a quadratic regression and so on and so forth. But what is important to us is this slide. Now how do we write this? So the way, this is how I'm defining it. So I'm writing h theta x1. So I'm writing at the first point x1. So I'm saying theta naught, theta 1 x1, theta 2 x2. So the superscript which you see here is the point, the first point where I'm finding this, and the subscripts which you see at the bottom is the dimension which I'm defining. When we had done it one dimensional regression, then we didn't have these guys. We only had these two, theta naught plus theta 1 x1, which we were referring to as alpha plus beta. Theta naught was alpha, theta 1 was beta. So you can write it as a summation. Now your h theta xi, this is the predicted value at the first point. This goes from how much dimensions to how many dimensions? It's actually written on the slide itself. Goes from d plus 1 to 1. Why d plus 1? Because you got theta 1, theta 2 till theta d. If d was 1, it would go from 2-dimensional to 1-dimension, which we saw in the 1-dimensional case, alpha and beta, where that's why g had become a 2-dimensional function of 2 variables, sorry. Everybody with me? Now what do? We have to take the difference of this guy from the actual value, sum it over all the point and minimize it. Same thing which we did. So that's written on the next slide. So we call it as a residue. We're taking h theta xi minus y. This is the actual value. This is the predicted value. Subtracted, squared. What I have done is put 1 over 2n in the front. Why I have done it? This is a normalization constant which you have put. It doesn't matter because there were n points and that may create trouble, so you divide by n. There is a square with a 2. When you take the derivative, it will cancel out, make your computation easier. So that's why I added 1 over 2n. Everybody with me? Now what will we do? Same thing. Take the derivative of this, make it equal to 0, and find the candidates for minimizer. So there are two ways of doing this. One, you can solve this minimization problem numerically. Another one is the closed form solution. The closed form solution which you saw in the one-dimensional case. Okay, I'll stop here. Rest of this then we'll do next Monday. We'll pick it up. Wednesday I'm not doing anything. Next Wednesday onwards I'll start taking optimization classes for you guys. This Thursday I'll email you where the lab is. But the idea is to get comfortable with Python. The resources are there. All tutorials from MIT and all those are there. So make sure you do. I'll come in the middle. Okay, thank you.